Let's go take a look at problem 112 on page 178. It's a good problem, uses some geometry here, and see how this will work out. And let's understand the problem. A rectangular package to be sent by delivery service can have a maximum combined length and girth, which is perimeter of the cross section, of 120 inches. Write a function for the volume of the package, all in terms of x. So we want to look at what the girth is. It says the perimeter of the cross section. So we're going to look at the girth, as I would say, would be, since this is a rectangular package, and it looks like we're going to have a square bottom. So the girth, I might say, is x plus y. It's the perimeter of the cross section is 120. Let's see how that works out. So we've got our sketch there, and I'm just going to redraw it just to get a feel for it. It's always good to practice just drawing these sketches a little bit. Not the perfect sketch, but good enough. Okay, so this is x here. This is x. All four sides are x. And we're labeling this as y. So I'm going to assume, based on what I think they're looking for, the cross-sectional perimeter of a cross-section. So I think it's going to be x plus x plus x plus x plus y. Let's just see if the girth, let's just see girth. We're not sure girth, but let's just see what happens. And I'm going to say the girth is 4x plus y. That's my interpretation of the girth. So we know that will be 120. So I'm going to write this relationship 120 is equal to 4x plus y. So that is what I kind of call a constraint equation. That'll help us out. Now it says write a function for the volume. Well, the volume for this is, remember, this is a prism, so it's got a square base. So the volume of this prism would be, remember, the area of the base times the height. In our case, y is the height. Okay, and the base here is going to be just x squared. So the volume now would be x squared times y. Problem is it wants it as a function of x only. I think what we're going to do is we're going to go ahead and look at this constraint equation, and we're going to solve that for y. And if we do that here, we can see that y is going to be equal to 120 minus 4x. So since y now is a function of x, I could substitute in now and make the volume now strictly as a function of x by writing x squared and then times 120 minus 4x. Okay, that's what I would go with. The next part of the problem says using a graphing utility to graph the function and approximate the dimensions of the package that will yield a maximum volume. Maximum volume. So really what we're looking for is we want to determine what this function is going to look like. Okay, this is going to be x. It's my input variable, which is one of the sides of my base, and the volume is going to be my output. Well, I know that if x is 0, the volume will be 0. So I've got this point here, and looking at this function here, I know that if x is, again, let's see, if this is 30, if x is 30, we'll have that. I'm predicting, since this is a cubic type function, it might get bigger, and then come down here. So that's part of that cubic function. And I'm really interested in the numbers between 0 here and 30. So I've got an idea of what my domain is for this problem based upon the function itself. And if that's the case now, notice if I put in here y couldn't have any height. So that could be a limiting factor. But the question is, what range would this be in? So what range? Because we're going to have to put this in our calculator. We're going to have to come up with some number. So why don't we just rough in a number? Just get a guess and see by putting somewhere in between here. An easy number that's not too far off. I could put 10 in. I could put 20 in. I'm going to try 10. So I want to know what would the volume be if I put in 10. And I could do this by hand. I could say 10 squared, which is 100, times 120 minus 40, which would be 80. 80. So I think my guess volume for starters would be 8 with 1, 2, 3 zeros. So I'm going to start a window that's going to be going from 0 to 8,000. We're going to see what that looks like. So let's do that. Let's get our calculator over here and let's turn it on and let's put it in the screen now and so we can see it here. And let's go ahead and clear my y equations and put in that equation. So it's x squared times left parenthesis 120 minus 4x. Okay, and we thought an appropriate window now would be x's would go from 0 to 30. And I'm going to put 5 for the increment. And the y's, we know it's going to have to go 0. And then maybe 8,000. And I'm going to go with 1,000 as my tick. And let's see what that equation looks like. Okay, needless to say, I haven't found the peak. I know there's a peak up there. So I'm just going to double that 8,000 and see what I find. So I'm going to go back to my window and put in 16,000 here. And maybe that'll be enough to see it. Ah, presto, I got lucky. I got it on the first try, and there's my graph. So I want to find the peak of that graph. I want to find where it's got the maximum. So I'm just going to do second calc. I'm going to hit maximum, which is number 4. And my left bound is, my calculator is to the left of the hump. So I'm going to cursor to the right side of the hump. And then all I have to do is cursor once in between, generally is good enough. Hit enter, and then boom. It says a maximum at 19.99999, a lot of nines, and it says my output is, wait, my output's 16,000. Well, hold on a second. That's what I guess my window would be. Did I get that lucky? Well, I think so. That's what the calculator says. Do we believe the calculator? Yeah, I think it's good enough. So we'll learn in calculus later on next year. That will probably be able to prove that another way, and it'll probably be valid. So I think that the maximum, a max occurs, okay, occurs when the side length, or x, is equal to 20, and those are inches, 20 inches. And the volume, the volume, or the maximum output, the volume is now 16,000 inches cubed. Okay, let's see. Did we answer the question what it asked? It said, use the graphing utility to graph the function and approximate the dimension of the package that will yield the maximum value. We did that. Okay, so find values of x such that v is 13,500. And which of these values is a physical impossibility? So really what we're looking for here is, it says, find when the volume is 13,500. And we're going to find the x value that makes that happen. Okay, for x. And we'd have to solve for x here. And I think a nice, easy way to do this would be use the calculator. Since we have this function already in the calculator, let's go and put another value in and suggest that we put in 13,500 here and then see where they intersect. Okay, we have two intersections. So let's look at the first one. The first intersection, I'll use second calc intersect, and the first curve is y1, second curve is y2, and I'm going to guess right where that one's at. So I get one value where x is equal to 15. and 15 inches, and that would be one value. Let's look at find the second one. Second, calc intersect 5 and curve, yes, yes, yes. And now let's guess over to this other one. So I'm going to guess that one. And that one says the x value would be 24.27. Okay, now let's see if these are valid relative to the girth constraint. So if I take x as 15, okay, I get 120 is equal to 15 times 4, which is 60, plus y. That means y would be then 60. Okay, and that would be my girth. Now the other case would be 120 is equal to, let's say, 4 times 24.27 plus y. And I have to figure out this one. Y is equal to, let's see this other equation here. I'm going to use my calculator to figure this one out. I'm just going to take 120. Oops, let's get out of there. Let's go to the home screen. 120 minus 4 times 24.27. That'll get us in the ballpark. And that means this is 22.92. 22.92. Okay, so that one seems to be another way of doing it for that one. So I could have two dimensions. Let's see, does that seem to work out okay? I want to figure out the volume is 15 squared, which is 225, times 6, 0, 0, carry through 5, 1, 3. That checks. And if I do the 24.27, and if I square that, I'm just going to check that, just double checking. I'm going to take 24.27, I'm going to square that number and times it by 22.92, and I seem to get 13,500. So that appears that those would be my dimensions for the package that would give me a volume of 13,500. Now it said that which of these values is a physical impossibility in the construction of the package. So there seems to be something that would constrain it, and the seems to be okay with those two values. So I'm not sure what they were talking about. So we'll go with this and we'll call it a day.